Hello guys, so today I'm going to be teaching you the first lecture, that is atomic structure, electronic configurations. I'm not going to be focusing on the lecture slides itself. I'm going to be focusing on the seminar slides, because seminars contains questions which are the replicas of the questions which are going to be coming in our SCTs, our final exams. So I thought that's going to be more important. So let's start. Over here we have the seminar slide, and we're going to just go through it, and I'm going to explain, and if I need another slide, I'm going to take another slide and explain to you guys. The molecular perspective of chemistry. Matter is the physical material of the universe. Matter is made up of relatively few elements. So basically it's talking about matter. Matter is all the substance around us. Everything around us is matter. So it's just saying that matter is the physical material of the universe. Atoms combine to form molecules. Atoms are the fundamental unit, okay, and then they combine to form everything around us. Then, as you see, molecules may consist of the same type of atoms or different kinds of atoms. Here you can see this is the ozone, so that's O3. You can see they consist of the same element or the same atom, you can say. Over here, carbon dioxide, that's a C, and then O2 over here, all that. Now, moving on to the next slide. Come on, we're going to talk about elements and compounds. Elements consist of only one kind of atom. So when you're reading the periodic table and you see the H, He, Li, all of these element names, so these refer to one type of atom and one type of atom only. Okay, they cannot be decomposed because they are the most fundamental unit. Okay, they are an atom in itself, and they cannot be separated or decomposed by any chemical means. Okay, they are the building blocks of the universe, and they are abbreviated by symbols as like I referred to: H, He, Li, B, Be, all of these things. Okay, moving on, we have compounds. Compounds are basically consist of two or more elements. Previous slide we just had over here, O3, that's a compound, CO2 is a compound, ethanol is a compound. Okay, they can be decomposed by chemical means into their respective elements, and we're going to see this in future lectures and future seminars where we talk about decomposition, we talk about when we talk about dissociation, all these different things, so we can understand how compounds break down into their elements. All samples of a compound will have the same elements in the same ratio. What this means is, let's say you have a huge jug of water, okay, and you have a small glass of water. The ratio of the elements in both of these containers of water is going to be same. It's going to be 2:1. Okay, H2O, two atoms of hydrogen for every one atom of oxygen. Okay, that's what's trying to say. Mixtures consist of two or more different elements or compounds physically intermingled. They can be separated into its components by physical means and often retains many of the properties of its components. Mixture is basically elements, fundamental, two or more elements from compounds, two or more compounds from mixtures. Boom. Moving on. Over here we have just this table which is giving us the mass and the charge of electron, protons and neutrons. These are the subatomic particles, meaning by subatomic particles I mean the particles which consist, no, these are the particles which an atom consists of: electrons, protons and neutrons. Okay, over here we can see we have the weight or the mass in grams. Okay, but when you're measuring stuff this small, we don't usually use grams. We use something called AMU. AMU is stands for atomic mass unit. And basically what atomic mass unit is, let's see, we have a carbon 12 atom, okay, C12 atom. Let's say we split that carbon 12 atom into 12 equal parts. Okay, we've done that, 12 equal parts. Now if we take one of those parts, okay, and measure the mass of one of those parts, we get 1 AMU. Okay, that is the scale with which you measure atomic mass units. Okay, so the mass of electrons, protons and neutrons being so small, we use this scale, that is AMU, and it's referred to, we can see what the weight of the electron, proton, neutron is with the AMU over here. That's 5.4 into 10 raised to minus 4, 1 and 1, basically 1 and 1. And then we have their charges as well. Electron, we know it's we can just say -1 +1. Okay, but when you're talking about, when we want to simply describe the electrons, protons, say +1 -1. But if you want to be really exact, we have -1.6 into 10 raised to minus 19 and +1.6 into 10 raised to minus 19 for protons. Okay, that's our table. Moving on to the next slide, we have the atomic number and the mass number. Very simple concepts. Let's just go right into it. Atomic number gives us the number of protons in the nucleus of the atom. Now, in a neutral atom, number of protons and the number of electrons will be the same. Hence, the fact that it's neutral, okay? Because number of protons, electrons is the same, they cancel out each other, and that's why it's neutral. Now, electrons can be removed from an electron from an atom with ionization, or electrons can be added to an atom as well. So, saying that the atomic number is the number of electrons may be wrong, because when you have an ion, then it's wrong, because the number of protons and electrons are not the same. So, just remember simple thing, okay? Atomic number is the number of protons in the nucleus of an atom. Boom. Moving on, mass number. Mass number is basically the mass of a nucleus. And what does the nucleus consist of? Protons and neutrons. Protons, we already know what that is. That's with the atomic number Z. Now, neutrons is N. So what is mass number? Mass number, mass of the nucleus, because if we remember the Rutherford's gold foil experiment, we discovered that most of the mass of an atom is concentrated in the center in a positively charged mass, that is the nucleus. So the mass number refers to the nucleus. Number of protons plus number of neutrons, that's the mass number, okay? And usually this is how we represent elements. This is how it's written in the periodic table as well. We have the element symbol, mass number on top, and the atomic number on the bottom. Okay, now you can see just example here. Boom. Now we can see a table here, okay, where this can be asked as an MCQ for an SCT or for example, and we can see here this is just a symbol for an element. We have carbon here, we have its mass number here, and we have the atomic number here. Very simple. They're gonna just ask us simple questions like, what is A? A being mass number. We already know what is A because it's basically given to us. It's on top, whatever's on top is the mass number. Okay, and then we have the atomic number, which is the number of protons, that's down. Now, the tricky part comes when they ask for the number of neutrons. It's not tricky, it's very simple. Some people will be tricky, but it's very simple. Let me explain. Now we know that the mass number is protons plus neutrons, and then the atomic number is the number of protons. So if we were to subtract the protons and protons from the mass number, then we'll be left with the neutrons. What I mean by this is, to find the number of neutrons in carbon, I just need to subtract 6 from 12, and I get 6 from 12. I get 6 again. That's the number of neutrons. Same goes here for this is fluorine, right? Yeah, fluorine. No, is fluorine? Yeah, it's fluorine. Yeah. Okay. Okay, sorry. Fluorine. That's 19 being mass number and 9 being the atomic number. So according to that, the neutron number should be, I expect that you said 10. I hope you did. Okay. If not, just go back. It's okay. Electrical charge remains 0 over here because we can see that there is no charge written on over here. Okay, otherwise there would be charge written here or something like that, but there's no charge written, so charge is 0. Now we have here Mg2+. Over here we can see the mass number is 24 and the atomic number is 12. Whenever you see an Mg2 plus or Cl minus, for example, don't think that the mass number and atomic number will change because of the fact that the element has a charge. The mass number and atomic number next to the ion will be the same as if it were not an ion, if it were an atom. But you have to calculate for the number of neutrons and protons example. You have to calculate by subtracting. Let me show you. Over here we see Mg2 plus, but the 24 and 12 would be the same even if this wasn't there, even if it was uncharged. Okay, so don't go thinking that, oh, since it's 2 plus, maybe this is different. No. Now 24 is the mass number and 12 is the atomic number, so the number of neutrons will be 24 minus 12, which is 12. Okay, but for the number of electrons is different, because since this has a charge, and that charge is Mg2 plus. Plus means it's positive. That means that the number of protons in this atoms are higher than the number of electrons. That means that if it's 2 plus, then it means that there are 2 more protons than electrons in this atom. Okay, so basically, to find the number of electrons, you just subtract the charge from the number of protons. The number of protons is atomic number, that is Z. So over here, according to that logic, then using 12 as our atomic number and 2 as our charge, the number of electrons should be, I hope you said 10. I hope you said 10. It is 10. Okay, and the charge is given to us. Basically, it's just like the mass number and atomic number. It's given to us, plus 2. Moving on to the next slide. Okay, we have the basic properties of electromagnetic waves. Let's talk about electromagnetic waves. We understand that an accelerated electron, look over here, an accelerated electron produces 2 fields, an electric field and a magnetic field. I don't know if you have learned this, but if you guys have learned the Fleming's left-hand, right-hand rule, it says that the velocity of electron goes in one direction, the electric field is in another direction, and then the magnetic field is in another direction, and you can see that all 3 of them are perpendicular to each other, all 3 of them, and that's how electromagnetic waves work as well. Over here, you can see that we have our y-axis here and our x-axis here. On our x-axis, we have our magnetic field component, and on our y-axis, we have our electric field component. Okay, basically the waves move like that, and the magnetic waves move like that. Okay, and the direction of propagation is perpendicular to both of the fields, electric field and magnetic field. Okay, and all these 3 components, that is the magnetic component, electric field component, and the direction of propagation, they're all mutually perpendicular. All 3 are perpendicular to each other. Okay, you can see here, I just wrote that down for you guys. Now, moving on, we need to understand some few terms. That's frequency, wavelength, and amplitude. Okay, frequency is the amount of waves traveling through a certain point. Let's say I take this point over here, just this point. The amount of waves traveling, okay, because you see the waves moving like that, like that, like that, like that. The amount of waves traveling to that certain point in 1 second is the frequency. Okay? Now what is the wavelength? The wavelength is the length between 2 crests or 2, what does it say? Hills, 2 hills, or the distance between 2 valleys or troughs. Okay, that's our wavelength. Now, if we have a higher frequency like that, we can see that the wavelength decreases here. By having a lower frequency, increases the wavelength. So what does this tell us? That frequency and wavelength are inversely proportional. Frequency inversely proportional to wavelength. Wavelength increases that means the frequency has decreased. Okay. Another important point, energy is directly proportional to frequency. Okay, just think of it like this. I'm punching your face. Okay, this is your face. I'm punching it, and I'm punching it at this rate. Or I punch it at this rate. What do you think was gonna hurt more? If you're smart enough, you would have said the second scenario, because of course frequency is higher in that, therefore energy is higher. This is just an analogy to remember the relation between energy and frequency. Now let's recap. Energy directly proportional to frequency, and we had learned frequency is inversely proportional to wavelength. Since frequency is inversely proportional to wavelength, that means that energy is also inversely proportional to wavelength. Understand? We're going to learn a few formulas later on, not now. Let's just scroll down, and we have a question here. And let's see. Which basic characteristic property of the visible light is changed if we change the intensity of light? Okay, and intensity over here refers to the amplitude. Okay, intensity, we're going to move on. You can see this slide over here. A higher amplitude results in a brighter light, and a lower amplitude results in a dimmer light. Amplitude is basically the intensity of a wave, not the energy. Energy and intensity are different. Okay, so basically the answer to this question is amplitude. Which basic characteristic property of visible light is changed if we change the color of the light? Now see, electromagnetic spectrum. We have spectrum which we cannot see, which consists of UV rays, X-rays, etc. And then we have a small portion from 400 to 750 nanometers called the visible range. Okay, now 400 to 750, you see how there is a range of wavelengths. Okay, 400 nanometer to 750 nanometers. So obviously the wavelength is changing. Okay, because if you're going to change the color, you have to change the wavelength. Okay, you can't have blue color at 400 nanometers and blue color at 750 nanometers. That's not possible. Okay, the wavelength and the frequency of the wave is what gives it the color and what makes it unique. But we also know that wavelength and frequency are inversely proportional to each other. If one changes, the other changes as well. We cannot isolate one. So that means our answer over here will be frequency and wavelength. Not frequency only, not wavelength only. And amplitude is not the answer, because amplitude just refers to a brighter blue or a dimmer blue. Okay, not a different color. Moving on. Next slide. Just refer to this. Now this is the spectrum I was talking about. This is the spectrum which we cannot see, and this is the small spectrum that we can see. I messed up, not 400, it's 380. But some books I have seen it written as 400 nanometers. But my bad, guys. Okay, 380 to 780 nanometers. Now we have a few formulas here. Okay, let's learn them. Over here, first we have C is equal to lambda nu. Okay, nu is the symbol for frequency. Okay, it's written like that, nu, and then this is lambda for wavelength. And C refers to the speed of light. You're going to see in future lectures as well. C refers to the speed of light. Okay, so the formula here is that the speed of light in a medium is equal to the frequency of the wave multiplied by the wavelength of the wave. Okay, I think I said this. Yeah, I think so. You can see over here, that's exactly that. Okay, and over here we get the C's value as that. Okay, speed of light, the 2.997, but you know how we take it. We take it as 3 into 10 raised to 8 usually, just to make it easier for us. So that's the speed of light exactly. Now moving on to the next slide, we have a few more questions. Let's solve them. What color light has the lowest energy? Now we had just learned energy is directly proportional to frequency. and frequency is inversely proportional to wavelength. I'm going to keep repeating this because it's important. Since frequency is inversely proportional to wavelength, energy is also inversely proportional to wavelength. Now, since they're asking for the lowest energy, that means we want to look for the highest wavelength. And the highest wavelength here is red. So the answer over here is red. Which color is decreased by the night mode of modern displays? Blue light. You're going to go to eyewear shops nowadays and you're going to see blue light blocking glasses specifically. That's a big thing now. So it's very common, it's just general knowledge, okay? Looking down, we have which forms of electromagnetic radiation can cause the following biological effects: pleasant warming, infrared, tanning, ultraviolet, serious tissue damage, x-rays. In later on lectures, we're going to learn how we can use UV rays, lasers, we can use it for carbonization of the tissue, vaporization of the tissue, cutting of the tissue, LASIK, all that good stuff. We're going to learn it later. Moving on to the next slide, over here we have a few numericals. Numericals are important. They're really simple. It's nothing to stress about. Let's see what the question is. Blue-green light has a wavelength of about 520 nanometers. Given to us is the wavelength. What is the frequency of this color? C, we know what C is. Speed of light 3 into 10 raised to 8 meter per second. So using our formula, C is equal to frequency into wavelength, that is C is equal to lambda nu. We can rearrange the formula in a way which can help us find nu, which is frequency. And that's what we've done here. Mu is equal to C by lambda. C we already know. Lambda we had nanometers here, 520 nanometers. Remember, when we're solving numericals, we need to make sure that the units match up. Since we're using meters per second on top, we need to make sure that we're using meters down as well. Now over here you can see how they've used 1 by 10 raised to 9, but I personally would write it as 520 into 10 raised to minus 9. Okay, nano is 10 raised to minus 9, and then you're going to get meters, then you're going to get your answer, and that answer is that. Over here they've given to us that 1 hertz is equal to 1 second inverse, so just this value right in hertz. Moving on, next question. It's like late now, but I'm going to start with the lectures. This is important. Okay, calculate the energy of a photon of excited Li atoms with the wavelength given to us. Energy is being asked. Okay, now in the previous slide we had the formula which I did overlook. I'm really sorry. Let me go back to the slide. E is equal to h nu, and E is basically energy, h is the Planck's constant, 6.626. I mean, it's different. Over here the textbooks have different values, so I'm gonna go ahead and see what it is, what I have written on the next slide. And nu is frequency. That's how you find energy. So again, using that formula, we're just gonna first off we're gonna calculate mu, because we need mu, and we're gonna do it the same way we did it over here, using mu is equal to C by alpha. Use that, convert the nanometers to meters, don't forget that. And once we have nu, just same thing, use E is equal to h nu, and h over here, as you can see, is 6.626 into 10 raised to minus 34 joule per second. And then we're going to get our energy value in joules. Now, the MRI body scanners used in hospitals operated with 400 megahertz radio frequency. Energy, how much energy does it correspond to in joules per mole? Now, we can find energy with the formula E is equal to h nu. Okay? Now over here, the question is asking per mole. Now that's a bit different, because when we're asking per mole, we want to use the Avogadro's number. So basically do everything the same way, but at the end, just use the Avogadro's number. Just multiply that with the Avogadro's number. And over here, again, make sure it says megahertz here. When it says megahertz, really make sure to use the convert it back to normal hertz, and that's 10 raised to 8 over here. Okay, so read the question carefully, read the units, and just think about, do I need to convert this, do I need to not convert this, and do that. Easy stuff, simple formulas where university students, we should be able to do this. Now we're gonna come to the absorption spectrum and emission spectrum. Now let's go up front a bit. I'm gonna explain the stuff to you, don't worry. Let's go back to Rutherford's model. We know the Rutherford's gold foil experiment, what happened, okay? Rutherford blasted a very slim gold foil with alpha particles, positively charged particles basically, and he observed a few things. Those few things were that the atom is basically empty. There is a large concentrated positive mass in the center called the nucleus, and there are electrons around the nucleus. And he created this model, and he said that electrons just revolve around the nucleus, just like how planets revolve around the sun. And he didn't really explain how this movement would work. Okay, Bohr, who used to actually work under Rutherford, okay, he said no, because if according to what you said, the electron revolves around the nucleus like a planet revolves around the sun, then it's gonna radiate energy. Why? Because in the previous slide, like I told, an accelerated electron produces an electric field and a magnetic field, basically EM waves. So if this electron is revolving around the nucleus, it's gonna produce EM waves. And if it does that, that means it's losing energy. And if it's losing energy, that means it's slowly gonna start revolving closer and closer and closer to the nucleus, because it's positively charged and electron is negative, so it's obviously going to be attracted. So what's going to end up happening is going to go revolve like this, emit energy, lose energy, come like that, boom, and demolish the whole atom. And then Bohr's like, how do you explain this? If that's the case, then no atom's going to exist. So Bohr said, let me make my own shit. Okay, so he made it. So let's see what he proposed, and this is what we use many a times to explain a lot of our topics, which would be hard to grasp if we use the quantum mechanical model, because that's like next level. So we still use this, although this is disregarded, we still use this to explain our brains, the concepts. So this is the model that he created. He said that there is one nucleus, and there are certain energy levels around the nucleus, and the electrons exist within these energy levels, and these energy levels have fixed energies, okay? And no electron can exist between these energy levels. If an electron is to exist, the electron should exist only on the energy levels, or in the energy levels, you can say. So when Bohr was criticizing the model of Rutherford, he made another point. I just made a point that it produces electromagnetic waves, it loses the energy, so it's gonna come down like that and hit the nucleus. But then Rutherford also said, okay, let's assume that happens. If that is to happen, then the electron is going to lose energy in a very smooth fashion. And when it loses energy in that smooth fashion, it's going to create a very smooth visible spectrum. Okay, while smooth visible emission spectrum. So basically it's trying to say that the emission spectrum is going to look something like this, since it's losing energy in a gradient. And if it's doing that, then it should produce a visible emission spectrum like this. But that's not what happens. What happens is this. The emission spectrum is in discrete blocks, and all this other is just blank. And there was no explanation for this in Rutherford's model. But in Bohr's model, right now, it does have an explanation. And the explanation is, look at this. Let's say an electron is here. It absorbs energy from external radiation and jumps up here. Okay, and that explains the absorption spectrum, why some blocks of light are not visible in the absorption spectrum. Is because they're being absorbed, and when they come down after excitation, they emit energy. Okay, they emit energy, and this explains the emission spectrum. So you can see here now, when we look at these diagrams again, we can see this is the wavelengths at which hydrogen absorbed the energy and the electrons went up to a high energy level. And after excitation, while coming down from the energy shells, they release energy, and this is what we get in the emission spectrum. So that's that. We explained that. We have a question here. Let's look at this question. Whose electronic transition that emits more energy than N3 to N1? 3 to 1. Difference of 2 energy levels. Okay. Now we just need to look at which option has a difference bigger than 2 energy levels. So let's look at that. N1 to N25. See, now, if you want to emit energy, you're going to have to be coming from a higher energy level to a lower energy level. Understand? Emit means higher to lower. Absorb means lower to higher. Okay? And because after electron absorbs radiation, it jumps up to a higher level. That's why. So the first option is negligible. Okay, we can neglect it because it's coming from a lower energy level to a higher energy level. So basically this is for absorption. This we can consider, but still this has only a difference of 1 energy level. So it's still not greater than the question. Then we have 5 and 3, which basically has the same difference between the energy levels. That's 2. And now finally we have 4 to 1, which has an energy difference level difference of 3. So yes, this is our answer. Now, state 3 basic principles that make up Bohr theory. Let's look at this. Electron in a hydrogen atom can move about the nucleus in any one of the fixed orbits. Like I said over here, any one of these fixed orbits. Only specific orbits with specific energies are allowed. So as I said, all these orbits have their own specific energies. The electron does not radiate energy as long as it remains in one of the orbits. So how does this solve Rutherford's model? Rutherford's model was it just revolves around the nucleus, emits energy, loses energy, smacks into the nucleus. But then, oh shit, Apple Pencil and my iPad, and I'm recording on my iPhone. So rich. I'm sorry. So, the electron does not radiate energy as long as it remains in one of the orbits. So now Bohr said, when an electron is in one of these orbits, it does not radiate energy. So hence, it does not lose energy and spiral down to the nucleus. Moving on, wave-particle duality. Okay, basically, wave-particle duality states that all matter in this universe has dual nature, and by that I mean particle nature and wave nature. Okay, De Broglie said, people say De Broglie, but I think it's De Broglie. De Broglie said that all matter in universe has duality, wave-particle duality. Even me, I have a wave function as well, along with the particle function. Everything in this world has duality. Okay? And how did he explain this? He gave us an equation. And he said that, where did it go? Here. Lambda is equal to, this is called de Broglie's wavelength. To find out the wavelength of the wave function, of your wave function. You can find out the wavelength of anything. This bottle. Stay hydrated. This bottle has a wave function. Okay, how do I find it? I'll tell you. Let's say I throw this bottle. I don't want to throw it, it's a really nice bottle, but imagine I throw it. I know the mass of this bottle. Okay, over here, to calculate the wavelength, I just need h, which I know, which is the Planck's constant, and then mv, which is the mass and the velocity. Mass of this, I know, it's like about kg. Okay, so mass I know. Velocity depends on how much I throw, with the velocity I throw it, and then I'll get its wavelength. Sorry. So you can see everything has a wave. Okay, and this property of everything having a wave is going to be really important in the future lectures, specifically electron microscopy, lasers and stuff. Okay, now giving some examples. Wave light, we understand the wave like functions of light in particular by the double slit experiment. We're going to read about that next lecture. And the particle nature can be expressed in the photoelectric effect, where the energy coming out of an object, of a plate in the experiment, is in a quantized package is called photons. Moving on, we have the wave particle. This is just calculating the wavelength, like I just did for my amazing bottle. Okay, that's that. The uncertainty principle. Okay, what is the uncertainty principle? Now, this formula right here, I don't really think is very important to learn, but just go over it, remember it, maybe. Okay. Now, it is not possible to know both the momentum and position of a particle with arbitrarily good position. Okay, I'm stood up because my ass hurts. Been sitting for a long time, and I had an 8 to 8 day today, so I've been sitting on my ass for the whole time. So yeah, now the uncertainty principle by Heisenberg. It just says that you cannot measure the momentum and the position of of anything at once. Okay, you just cannot, because it is because of the duality of matter, wave and particle. Okay, particle basically states that an object is present in one place with respect to its space, at one point with respect to its space. That's what we define as particle functions. But waves do not exist in one place with respect to its space. Okay? They're everywhere. They're going. Okay? That's waves. So, if everything has duality, that means that the particle and the wave nature exist at the same time. So you can understand, if particle says that the particle nature suggests that the material stays at one place, but then the wave nature does not suggest that, we can understand why the uncertainty principle exists. Okay? So that's the uncertainty principle. Had enough of that standing. Okay? And yeah, it's a very cool thing to know. Carved on the gravestone of Werner Heisenberg, who proposed this. He lies here somewhere, which is really cool. Okay? Really cool. It's like, that's the sickest quote ever to put. I lie here somewhere. Okay? Moving on, Erwin Schrödinger briefly discussed quantum mechanical model of the atom. The quantum mechanical model of the atom, you can see in the lecture slides. Okay, it's at the 10th slide or something like that. But what is it basically? The quantum mechanical model is the final model that we are using right now. Okay, it's come after centuries and centuries of experimentation. We had Dalton's model, we had Rutherford's model, we had Bohr's model, and then now finally we have the quantum mechanical model. Okay, the quantum mechanical model basically does not follow Bohr's principle, where it says that there are certain energy levels where an electron can exist. Okay, where it can be found, but there's a cloud around the nucleus, or spaces where electrons can be found. Okay, that's where we get the s orbital spear shape, p orbital dumbbell shape, d orbital double shape. These are the places where the electron can be found. Okay, Now we have some big boys, quantum numbers, the big people. Now let's just study this in my way. Okay. Now I've given some examples up top of how we can what do we say, describe the position of an electron in an atom. This is one of the ways. Let's start with the first one. That is the principal quantum number, which is the boss, it's the head. After that, below that are the levels. Okay, so we can see over here principal quantum number that is denoted by n. It can be 1, 2, 3, 4, 5, whatever, going on from 1. Second, now n gives us the energy level. Okay. Now second, the quantum number is called the orbital shape number or subshell quantum number, and is denoted by L. Now this is very different. This is very unique. Look at this. L's values start from 0 and go up to n minus 1, and n is what? The principal quantum number. So let's say the principal quantum number is 5. Okay, that means L can be from 0 till n minus 1, which is 5 minus 1, 4. So it can be 0, 1, 2, 3, 4. Understand? That's the one example. Now, each number on this L, each number on L represents a shape of an orbital. And how I remember this is I use this mnemonic. Smart people don't fail, and we're smart. We ain't gonna fail. Fives only, gang. Okay. So I write SPDF, and then I just write 0, 1, 2, 3. That just helps you remember. So 1 refers to the p orbital, 2 refers to the d orbital, 3 refers to the f orbital, and 0 refers to the s orbital. Let me show you the shape of the orbitals real quick. There we go. S has a spherical structure, P has a sort of a dumbbell structure, D has sort of a double dumbbell structure. Okay, and F over here, I don't even know what shape that is, just like porcupine type thing. Okay, but you get the point. Now the next number that we have is magnetic quantum number, M subscript L, M small l. Okay, and the values of ML are from minus L to plus L. So let me give you an example. L's value is 2. 2 refers to d orbital. D orbital. 2 refers to the d orbital. Now, if L is 2, then ML will be from minus 2 to plus 2. That is basically minus 2, minus 1, 0, 1, 2. All these values apply. Okay, and this also helps us to tell the number of shells in an orbital. When I'm going to be drawing the orbital diagrams, it'll help you. I'll explain to you why I'm saying that. Finally, we have the magnetic spin number, which is just plus half or minus half. We need 2 electrons to cancel out their spins to maintain net zero spin at all times. Next up, what do we have here? Each subshell is made of. Okay, there's going to be questions in the MCQ like this. Okay, they're going to give you a subshell number, and they're going to be like, how many orbitals does this have? So we need to learn this formula, that is 2L plus 1. Let's say the number of n is 4. So the number of orbitals in this will be 2L plus 1. Now I give you the value of n though. N is principal quantum number. So if n is 4, we know that L can be anything from 1. No, L can be anything from 0 to 1 to 2 to 3. N minus 1. Remember? 0 to n minus 1. So now we have our values of L. Okay, that's ranging from 0 to 3. So now you're going to ask me, okay, the formula says 2L plus 1. Which value of L should I use? Okay, now you could use any value hypothetically, but then we usually use the highest value Why? Because that just tells us the maximum number of orbitals that subshell can contain. So usually in MCQs, the question is going to be like, how many orbitals are present in third subshell? And you're going to be like, okay, fine, but what value of L do I use? Because it doesn't say maximum. When the question asks you that and it doesn't mention maximum, you still use maximum and be like, this is the maximum number of orbitals a subshell can hold. So basically, if n for me right now is 3, my L's can be 0, 1 or 2 because n minus 1. L is 0, 1, 2. If I want to know the number of maximum orbitals that can present in n equals 3, I just need to do 2L plus 1. And the maximum number of value of L was 2. So 2 into 2 plus 1, that's 5. Boom. See this now, there's going to be questions here. Was there no questions here? There are going to be questions later on. Quantum numbers and subshells, you can just see here. When n is 1, possible values of L are 0 because you can just go from 0 to n minus 1. I'm just gonna remove my AirPods here. I'm hoping that my iPad still works and the mic is still sick. Okay, I'll just turn off my fan. That might be interfering with the noise. What is that? We have noise in my house. Okay guys, whatever. Yes, so that's that. Quantum numbers and subshells. Over here you can see the value of n is 2. So possible values of L are 0 and 1. And that's how we get all of these. You can just look at this table. This table is really nice. How many electrons are found on a p subshell? Now, look at how I'm calculating this. Look at my thought process, okay? P. When I see P, I write S, P, D, F, and I write 0, 1, 2, 3. So now I know P is 1. I know P's value is 1. And what is that 1? That's the L. That's the shape orbital shape number. So I know now L is 1. Now if L is 1, now I need to find the ML. ML is going to be from minus 1, 0 to plus 1. So I have 3 values for ML. And ML determines how many boxes there are in the orbital diagrams. So how many electrons are found on a p subshell? So I'm going to draw the p subshell. I know there are 3 values of ML, so I'm going to draw 3 boxes. And then I'm going to start filling. 1, 2, 3, 4, 5, 6. 6 electrons. Boom! How many electrons are found on the second shell? Orbitals are found on the second shell. You see this? Second shell is n is equal to 2. Okay? That means L can be 1 or 0. The maximum value of L is 1. So using the formula 2L plus 1, we get 2 plus 1, that is 3. What is the lowest possible number of ML on the 4F subshell? Look at this. 4F, 4 being the n is equal to 4, principal quantum number is 4. F, S, P, D, F, 0, 1, 2, 3. So F is 3. Okay, if the value of L is 3, okay, that means ML is going to be from minus 3 to minus 2 to minus 1 to 0, 1 to 2 to 3. These are all the values of ML. My lowest value is minus 3. Boom. What values of the subshell quantum number correspond to the following subshells? The answers are given. Pretty easy question and answers, guys. Please go through it. Not that much. Very easy and understandable. Okay. Energies of orbitals. Orbitals on the same energy level are called degenerate. That's just one term. It's probably going to ask in an MCQ. They're going to be like, orbitals on the same energy level are called what? You're going to say degenerate. Okay. This is how electron configurations are written. Principal quantum number. This is the value of L. Total number of... Now I'm going to tell you how to fill out, how to write electronic configurations. I'm going to explain to you now. Let's take this. Let's take an atom X with the atomic number 16. I don't know, let's take 16. That means the number of electrons is also 16. Now that's also 16. Now Let's start filling this out. Now, you see this table that I've drawn here? This is how you should write or draw next to your paper or something. I don't know, use iPad. Everyone uses iPads now to fill out the electronic orbitals, or you can remember this. And how do you start filling? Let's see. It goes diagonally. So 1s first. So you write 1s, and then an s orbital can hold up to maximum of 2 electrons. So write 1s2. Now out of the 16 electrons, you have done 2. Okay. Then you go like this. 2s. Okay. And you go 2s. Maximum number of electrons s can hold is 2, so 2s2. Now out of the 16, you have done 4. And then you go like this. 2p and then 3s. So you go 2p, and we know the maximum number of electrons p can hold is 6. And then you go 3s2. So that's 1, 2, 3, 4, 5, 6. That's 12. We need 4 more. Okay, electrons. So keep filling. Now you're going to go diagonal again. We're going to go like that. That's 3p and 4s. Fill out again. 3p. Now I could write 6. But I don't need 6. I just need 4 more electrons. So that is how to write electronic configurations. Okay. Now I'm going to also teach you how to draw orbital diagrams. Okay. Let's say I'm just going to draw this out for you. So it's going to be easy. An s orbital is going to have 1 box. A p orbital is going to have 3 boxes. I'm going to explain why. A d box has a SPD 0, 1, 2, 5 boxes. And finally, an F shell is going to have FB4, 6, 7 shells. Okay? So now that we know this, I'm going to tell you why. Because we know that L value is equal to 0, 1, 2, 3. We've done this. Now if you know L, now we can also write the values of ML. And since ML is, for over here, if I write ML, it's going to be just 0 because the value of L is 0. And the value of ML goes from minus L to plus L. Then we have 1. So that ML is going to be minus 1, 0, and 1. And for D, since it's 2, it's going to be minus 2, minus 1, 0, 1, 2. And for this, it's going to be minus 3, minus 2, minus 1, 0, 1, 2, 3. You see how the number of values of ML correspond to the number of boxes in the shell diagrams, orbital diagram. That's how you just know. Okay. Now let's start filling these orbitals. Okay. Let's take, for example, this shell. Let's take, for example, this. Okay. We're gonna draw this something like this. 1s first. Then for 2s, we're gonna draw another s orbital. Then for p, we're gonna draw another orbital. Okay. This is I'm doing this one right now here. Okay. Let me just move that actually. Wait. To P, 3s, draw another small box. For 3p, draw another 3 box. Now boom, 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 boom. Let's start filling these electrons. These shells. So for S, we know that the maximum electrons that it can hold is 2. So fill them out like this. 1, 2. Okay. And this one, 2 again. So 1, 2. Now see how I'm filling this. Okay. See how I'm filling this. For 2p6, I'm gonna go 1, then 2, then 3, then come back 4, 5, 6. This is a rule. This is a rule, very important rule. And that rule is the Hund's rule. Electrons, single electrons fill each orbital singly before any orbital gets a second electron. Okay? So this, just 1 and 2. And this, remember again, 1, 2, 3, 4, 5, 6. Please don't do this. Please do not do that. Doesn't make sense. So what you want to do is this. Okay. So now I'm told to draw the orbital diagrams. That's basically the next slide. It's gonna have ask some MCQs. I'm gonna show some example diagrams of the orbitals, and that is basically the first lecture, guys. I hope you had fun. I hope you understood. That's me. My name's Arham. I'm the Clutch Indian guy. I'll see you in the next video.